Okay, I will just skip some of this. These are just some of the basic energy concepts that I had wanted to walk us through. But you already have these materials. You can go through them. If you have questions, you can come back to me on this. So like I said, those were just basic introduction that I had wanted to do. So let's get straight to the solar PV design. So like I was saying, that solar PV, as most of us know, it is also known as photovoltaic, and is a technology which generates electricity directly from the sunlight via photoelectric effect. The photovoltaic module, which is made up of photovoltaic cells, transforms solar energy into DC electricity. Now we must know that PV modules, they generate DC form of electricity, not AC form of electricity. And DC means direct current. I'm going through all of this because I know some of us are already very aware of this, as well as some of us may not have the basic understanding of solar systems. So please, if you're already far ahead of this, please bear with us. Let us carry everybody along. That's the purpose of this. Okay.
And we resume recording.
Okay, Uche, please, can you do that? Oh, thank you very much for pointing that out.
I've done that, sir. It's been recorded. Go ahead.
Okay. So, like I was saying, there are two forms of electricity. There is DC, two forms of current. There is a DC current and there's an AC current. So the solar system, the way we know them, produces direct current. So direct current will not be able to power your conventional electronics in the house. Okay, so to get that kind of current, you need an inverter. We'll get to that. But the point here is that there are two forms of energy you can get from the solar system. One of them is the DC current, and another one is the thermal energy, solar thermal energy, which produces hot water. These are two different forms of energy from the solar system. So the diagram that you're seeing here, the first diagram that you're seeing here is the solar panel, and the second diagram that you're seeing here is the solar thermal that produces hot water. So it uses energy from the sun to produce hot water, whereas this one uses energy from the sun to produce electric. So it is important to make a clear distinction between these two very different technologies, which are often confused since they use the same energy source. So solar electricity generated using PV can be fed into electricity grid, stored in batteries for later use, or used directly. As of 2018, the total global installed PV capacity was approximately 390 gigawatts. This more has changed significantly. So here is just a pictorial representation of the two forms of energy sources directly from the sun. This what you're seeing here is a solar array producing DC current, and what you're seeing here is a solar thermal producing hot water from the sun. So there are two different major configurations of PV system. You have the off-grid, I have the on-grid or grid connected. So your solar systems can be off-grid, or you can connect them to the grid. So for the off-grid system, you can see the diagram by the left here. You have the solar panel that is now connected to a charge controller that is connected to a battery system. Then, of course, an inverter before it powers your load. Then for the on-grid system or grid-connected system, in most cases, you don't need battery. So the solar system produces DC current, you convert it to AC current, and you feed it, you export it to the grid. So these are the two major differences between the grid-connected and off-grid system. We'll see more examples of this. So we have the PV off-grid, and we have the PV grid connected. So for the off-grid systems, you have PV system for rural electrifications. Now, most rural communities are not connected to the national grid. So for those kind of communities, it becomes best and becomes more viable to connect them using solar systems for off-grid electrification. So these systems, most of them, like I said earlier, have battery. In fact, when you're doing an off-grid solar system, most of the cases you have batteries integrated into the design. So systems with these systems have batteries. And the reason why I'm saying most of the time you have batteries integrated into the system is because in recent time, we are beginning to see inverters for off-grid systems that can function without batteries. Okay, maybe one of our resource persons might be able to talk about it, or when we go for a site visit, you'll be able to see some of these inverters that can function without battery, yet they are off-grid solar systems. But for most of the off-grid systems, there has to be batteries. For most of the off-grid system, there has to be battery. So there are also systems without battery. Now, in this case, when we are talking about systems without battery, we are making reference to solar water pump. Solar water pump. Solar water pump does not need battery. Okay, and for many of them, they use DC current. So you don't need an inverter to convert them from DC to AC current. So while the sun is shining, they can pump water directly. When the sun is not shining, they stop pumping water. That's the characteristics of solar pumping without battery. So we have the standalone mini grid. You may have had so many conversations around mini grid in Nigeria, maybe the deployment of mini grid in some rural communities to electrify them. So this is a typical example of an off-grid solar systems. So some of the examples of standalone mini grid is purely PV system, where you have a PV system with storage to provide electrification for rural communities. And then you have a hybrid system. In this case, you have PV system, you have solar panels integrated with maybe diesel generator, because of course, sometimes there might be, the sun might not produce adequate energy to supply to the community. Then you have to come up, you have to kick in your diesel generator to come in and then provide that electricity. Or sometimes the electricity that is being stored in the battery may run out during the evening time. And of course, you don't want to leave the community in darkness. So diesel generator have to come up to provide the required electricity at that point. And that's the reason why hybrid systems are more robust. They are more stable in terms of providing electricity for rural communities, as opposed to only PV system. If you're doing only PV system or purely PV system, you may need to have adequate battery storage. Even at that, there may not be guaranteed that there will be constant electricity, because there could be a time when the batteries might be drained, or there may be a fault somewhere whereby you need to keep the community constantly powered. In those cases, you have to now call for your diesel generator. So there are also large PV diesel hybrid mini grid for industrial applications. Now, there are some industry that's not necessarily need to connect to the grid, in which case they now integrate solar PV systems with generator, and they are off and they are good to go. They don't need to connect to the grid. So if that is the configuration, if you see such configuration, it is also PV off-grid system. So let us look at the PV grid connected system. So there are distributed PV systems feeding electricity onto the low voltage grid. We have different levels of voltage in our grid system. We have the high voltage up to 330 kV lines. We have 132, we have 33, we have 11 down to 400, and then the one that fits into our house, which is 230 volts. So the PV grid connected systems feed into the low voltage grid. When I talk about the low voltage, essentially maybe around 11 kV, depending on the voltage you need to use that electricity, or the 400, or even the 230 volts that we use in our various homes. So in some cases, you have this PV system on the roof of our buildings. You could have them on the roof of our buildings, in which case it's feeding directly into the home appliances. We're using them to power our appliances in the home. But because they are connected to the grid, the excess energy generated is fed back to the grid. It's sold to the grid. It is not common in Nigeria, but in some other advanced countries like Germany, it is very common, where people can have solar panels on their roof and they sell the energy, excess energy produced back to the grid. So that is also an example of grid connected PV system. Then we can also have it at a commercial level. You could have industries that have solar PVs for their own consumption, and they can also sell the excess back to the grid, or even not necessarily an industry. You could have solar system in a particular region and you're selling all of the energy to the grid. Okay, so that is commercial, and of course, maybe industrial solar PV installation that are connected to the grid. Then we also have another form of grid-connected solar system, which is the central PV system, feeding electricity onto the medium voltage grid. Remember, I had mentioned that we have different levels of voltage in our grid network. So this central PV system is feeding into the medium voltage, maybe at 33 kV. Yeah, I think it's from 33 kV, you can feed in solar system into the grid at that level. So now, in many of these cases, you have the large-scale PV plant, or some of them that we prefer to call solar farm. So you have a large PV installation, and they are feeding directly into the grid. Okay, so all of these are examples of grid-connected PV system, and the ones by the left are examples of off-grid PV system.
Hello, excuse me, Chima.
Okay.
So that means basically PV applications are divided into two broad sense: off-grid and grid-connected. And in the off-grid, there are three subsets: the ones that are PV system for rural electrification, which also have two subsets, those with batteries and those without battery. Then we have the standalone mini grid, and then we have the large PV hybrid mini grid. And then for the grid connected, there's two sets of them: the central PV system, which you refer to as solar farms, especially mainly seen in European countries, and the distributed PV system, which is more like the one we're doing in Nigeria now, on off-site locations. Okay, so it's good to really draw attention to that, so that whenever our participants see some of this solar installation, they can easily say this is what it is and identify with it, as well as those who might go to do certification exam. These are kind of things that they are asking the exam. Thank you.
Okay, thank you very much for the contribution, Engineer. In summary, you've just said it. I mean, you've just summarized what this is all about. In broad category, there are two different categories of PV application: the off-grid and the on-grid. And you have the breakdown, as you can see from the screen. So let me just proceed. So let me talk more about the grid-connected configuration. So the grid-connected configuration can have various sizes and will be located at different points in the central electricity grid. Remember, when we talk about grid, it means that there are so many, several generators connected to a central distribution network. That's what the grid means. So when we're talking about the distributed PV system, distributed means that you can have them in several locations and several sizes, but they are all connected into the same distribution network. So they are all feeding into the same distribution network. And the person who is using it might be at a different location. As long as the person is on the distribution network, the person can be able to use that energy. So distributed systems are typically constructed on residential, commercial, or industrial buildings. Systems on residential buildings are usually small rooftop systems generating electricity for private consumption or for sale to the electricity grid. I've explained this before now. Systems on commercial and industrial roof are also used to either offset on-site electricity consumption or to sell electricity to the utility. However, commercial and industrial systems are often much larger than the residential systems. Distributed systems are usually connected to the low voltage distribution grid. In all grid connected systems, the PV array, sometimes referred to as the solar generator, of course, this figure by your right typically shows that. So this is a typical residential PV system. It generates DC electricity and is connected via a junction box to an inverter, which converts the direct current into an alternating current. The inverter output is connected to a meter which records the amount of energy being fed into the grid. So if you're going to send any energy to the grid, there has to be a meter to capture and measure whatever you're sending to the grid. This is very, very important when you now have to do the financial settlement. How much energy have you fed into the grid so that you can be adequately paid for it, depending on the arrangement you have with the distribution network or the people that owns the grid network. So there are also central PV systems, like I mentioned the other time. Now, these are also known as solar farms, solar parks, or utility scale PV system. Large scale PV power generation is concentrated at one specific location. Such plants can take up to large areas of land and fit directly into the electricity grid. The configuration of such plants is more comparable to conventional power plants, producing three-phase power. They are connected to medium or high voltage transmission network. All these are just to give us the basics of how solar systems are designed and the various applications. And before we now get into the components and how you can be able to connect all of these components together to achieve the desired result. So this is a schematic of a grid-connected PV system. Now, for a grid-connected PV system, remember that one of the key features is that it does not necessarily need a battery to function. If you're connecting a solar system to the grid, you do not necessarily need a battery. You can have a battery to store energy that you can use during the during the evening time. But in most cases, you don't need a battery for a PV connected system, and it's a very good advantage because it reduces the cost of of the project. The cost of battery is so much that it can take up to 50% of the capex of the project. But when you take away battery, it becomes more viable, and that is why grid-connected PV systems are more suitable for the large application, for the industries, for the commercial. And if you go to some advanced countries, they have also been able to use this technology at a lower scale for homes, for residential buildings. So you have the PV that produces the electricity, and like I said, the electricity is a DC, is a direct current. So you need an inverter to convert it from DC to AC on alternating current. And then you need a meter to measure the amount of energy that you're producing, and then you feed that into the grid. So for an off-grid configuration, you need a solar panel that will now go into a charge controller. Now, when you're bringing in batteries into the design for an off-grid configuration, when you're bringing in battery, the battery also comes along with what we call the charge controller. The charge controller. I will get to discuss more about the charge controllers and why you need the charge controllers. But let me just give a brief understanding of what the charge controller does here. Because these batteries need to be charged at a constant voltage. Your batteries need to be charged at a constant voltage. Now remember that this is your solar panel. It produces electricity at a varying voltage depending on the intensity of the sun and the temperature of the panels. It produces electricity at different voltages. So what this charge controller does is that it helps you to stabilize the voltage that is going into this battery. And that's why when you're installing batteries to a solar system, you need a charge controller. Someone has raised his hand. You have a question? John.
Yes, I have a question, and my question is the reason I'm interjecting because I see that we are giving the introductory part of the grid. So because the grid connected option, my question is related to that.
Okay.
So I have a situation where I'm actually running a POC.
Okay.
For now, a typical office that have a 250 kVA generator during regular run and a 100 kVA generator during off-peak, connected to grid. So the POC we are running is looking at connecting a grid interactive inverter.
Okay.
Actually connected. I was at the site yesterday and it's running, but I see a major challenge, considering the fact that grid availability is probably between 40 to 60%. So I see end up running a large portion of the period on generator.
Okay.
With my current presentation, for instance, in the afternoon, when my generator is configured to be on a bigger generator, I was having a very large contribution from the solar, and the generator ended up being when the grid power went off and generator peak, the generator ended up running at a very low
load factor,
presenting me with another problem. Then now I'm not sure. I mean, we are looking at that. If I change the generator, I may still run into problem by the time because it's an office where people sit. Compressor may increase and other stuff. And now I'm seeing a lot of complexity. So I'm just wondering, does it make any sense at all to even run a grid connected without battery in a Nigerian setup that we don't have regular grid?
Okay, in your own case now, you don't have batteries. It's just interactive inverter with the grid, and of course, you have a generator forming grid in the system as well. Correct?
Yes.
Okay.
My major problem is when I'm running generator. Because
I understand. I understand. So when you're running generators, because you have a large contribution from the solar system, so your generator is running at a very low load factor and is affecting the generator. Hello?
Yes, correct. That's the scenario I have.
Okay. So the thing is this: at the time you are doing the design of this system, there's a minimum load requirement for that generator to run, which is in most cases 30%. So you could have, while you are doing the configuration, you could have set that minimum load requirement so that your generator cannot run below that 30% load factor. Now, if it gets to that 30% load factor, what is going to happen is that it will derate the input from your solar system, which means some of the solar energy that is generated from your solar system will become redundant, which is not very, very efficient. I mean, for this kind of design, right? So that's what can happen. There are some of these inverters that you can actually program to do this. So I don't know the kind of inverter that you have. I don't know if how you were able to program it.
Okay, I think that answered the question. That yes. Derating of the solar from the by the inverter programming, it answered the question because exactly. That is the argument I was having with the vendor yesterday, that the solar will always contribute whatever is available. So I think that maybe the inverter is using does not have that. I think that is the problem. That answered the question.
Exactly.
Thank you.
Thank you so much, too. I think, did someone else raise his hand? Okay, let me just continue. Okay, Emmanuel.
Yes, okay. It's me, sir. It's about the off-grid system. I'm trying to imagine it from my own end, how you can sell through grid system as an individual.
You can do what? How you can do what? Sorry.
Energy, or as on-grid system here in Nigeria, not the one you're using at your home or in your office. Hello.
So the question you're asking is how you can sell your excess energy to the grid.
How you can connect it. Let's say in an area, just an instance, in an estate where you live, you have an intent to run such business. And let's say the distribution company here in Nigeria, precisely I mean in Abuja, you want to come up with such proposal. How can you go about such? Here in Abuja, most buildings come in form of estates, not like duplexes, as individual houses.
Yeah,
how do you, as an individual, go on grid? Solar energy system here in Abuja.
Yeah, I understand. Thank you. Okay, go ahead, Richie.
Let me just answer that one quickly. I think the challenge of that one is our grid. We don't have a smart grid yet.
Exactly.
But somebody is also suggesting that maybe we can leave the questions, most of the questions after the class, since we have only 2 hours and we have quite a lot to cover up today. So let me grab the indulgence of the people. The training is okay. The questions are very good, but let's note them down. Have a list of questions. We're going to reserve the last 10 minutes for question and answer so that let us cover what we need to do for today, because the whole 5 week is full of activity. Okay, there's no space. So please, I crave for indulgence. Let's try that model. Thank you.
Okay, thank you very much, Engineer. I think you've answered it. We don't have a stable grid in Nigeria, not to talk about being smart. So it becomes difficult to do that in Nigeria. So we may not be able to do that for now. So now this is an off-grid configuration, and I think I've explained how this applies in the sense that you now have to bring in battery and then you bring in a charge controller. This is the major difference, and of course you're not feeding it to the grid. It's disconnected from the grid. So this is just what an off-grid system is. So this is an off-grid system, but this is for a micro and mini grid, in which case you're generating that electricity from a central point and you're distributing to a community. However, this community is not connected to the main national grid. So let's also talk about the components of a PV system. So from the primary component, which is the solar cell, this is a picture of a selected technical characteristic of silicon wafer-based and thin film solar panels. Now, if you look at the screen, you're going to see 3 sets of solar panels. In this PowerPoint presentation that I was going to present, I had removed this slide because there has been some advancement in solar technology, and we are bringing in somebody to come and update us on that. Okay, so if you look at some of the research that has been, some of the statistics that has been thrown up here. Okay, let me just run this because this used to be the market situation, but it would have changed by now. So the first cell you're seeing by your right is the polycrystalline panel. The one in the middle is the monocrystalline panel, and then you have the thin film panels. So they all have different efficiencies. The polycrystalline has up to 18% efficiency. The mono has 22% efficiency, and then the thin film has 17% efficiency. They all have their own advantage and disadvantages. So in terms of power temperature coefficients, there's a place we'll talk about this power temperature coefficients. So I don't think it's appropriate for me to, because it will lead to a lot of confusion. So let me just ignore this slide. We'll get to a point where we'll talk about these things individually. Then the market share that you're seeing here, this is one of the reasons why I say that I no longer believe that this market share is valid at this time. This research was done sometime in 2018 to come up with a market share of 62% for the polycrystalline and 32% for the monocrystalline, but that has changed now. There has been a lot of innovation in the monocrystalline panel, and there has been a lot of deployment of monocrystalline. I doubt if people still buy poly. So let us just leave this slide because it's a lot of, some of the factors has changed. We are bringing in somebody who works in the solar industry, in the manufacturing of solar industry, in the solar panels, sorry to say. So he will update us more on this. So let us look at the arrangement of the modules of the cells. So every PV module that you see in the market is a combination of PV cells. So what you're seeing here, this box you're seeing here is a PV cell. So every module is a combination of several of these cells. And that is what we call module, PV module. When you now arrange these modules in a project, it becomes arrays, solar array, okay? So let us understand some of these terminologies: PV cell, PV module, and PV array. So PV modules are formed by connecting PV cells in series or in parallel and encasing them in a protective material. That is a PV module, the one you're seeing in the middle. PV modules can also be connected in series or in parallel in order to form a PV array on the roof, what you're seeing on the roof here. So the number of modules determine the maximum power generation capacity of the plant. Of course, if you have more PV modules, you have more electricity generated. If you have less number of PV modules, the less number of energy you will generate. So that's PV modules. Now, from the PV module, we move to inverters. Now, inverters they are just converters. They convert electricity from direct current to alternating current. That is their work. Okay. So an inverter converts direct current input from the PV array or battery into alternating current. Alternating current is the basic form of electricity that we use in our homes. Why direct current is the kind of current you get from batteries. If you remember, you cannot just take battery and use it to power your AC, your fridge or your television. And of course, I know there are DC televisions, but in this case, I'm talking about the conventional televisions that we have in our home, which is the AC television. So to convert the energy from the battery, which is the same form of energy that the solar panel produces, we need an inverter to change it from DC current to an AC current. That's the whole essence of having an inverter. So this is the sun, this is the solar array, and this is the inverter. So this equal sign that you're seeing here is used to represent a direct current, whereas this other sign is used to represent an alternating current before you can either feed it into the grid or for your home consumption. So that is the work of an inverter. So we have different kinds of inverter. We have different kinds. So we have a micro inverter, we have a string inverter, and we have a central inverter. So inverter can be connected at different points of your design, of your solar PV design. You can put inverter on the panel. So the moment the electricity is, the energy is generated by the panel, it is converted from DC to AC at the panel level. Okay. So if you have that, that's what we call micro inverter. So alternatively, you can collect some of this DC current and then feed, the DC current, you can collect it from several PV modules and connect it to one inverter. You collect the energy from several PV modules and you connect them to one inverter. Okay. So if you do that, you have a strange inverter. So you can have several strange in a project. For a large scale project, you can have several strange inverters in the project. Okay. And then lastly, you can have a central inverter. A central inverter, you're connecting all the whole PV modules to one inverter. Even if you're doing a 2 megawatts project, you're connecting every one of them to a central inverter. Okay, so these are different types of inverter that you can use in the project. Of course, there are some other kinds of inverter that now depends on the function. There are interactive inverter, like one of our colleagues mentioned in his project. You have an interactive inverter, but that name interactive is because of the function that it does, okay? And not necessarily at the point where you place it in your project.
Dinachima, we've lost you.
Recording has stopped.
Okay.
Okay. Now, for most of the buildings where we are going to be doing this solar installation, at the time when these buildings were designed, there was no consideration that solar panels were going to be mounted on the roof. And that's where, for most of us who are engineers, you need to be very, very careful when you're doing your installations. You can go and install a solar panel on a building that is already weak, and the weight of that solar panel might be able to affect the structural integrity of that building. So we must pay attention to the structure you're mounting the solar panels. One of the solar panels of about 400 watts weighs as much as 20 kilogram or 20 something kilogram. Okay, that is half weight of a bag of cement, right? Or just one of the panel. And you cannot imagine where you're not having several number of these panels on a roof. If this building has not been designed to withstand such weights, it's going to affect the structural integrity of that building. So if it is not possible to put all the panels on the roof, you may need to consider ground mounts, mounting the solar panels on the ground. So these are some of the things that we need to look at when we're looking at mounting structures. Since large array structures, including the modules, are heavy, it is necessary to seek the advice of a structural engineer prior to roof mounting. The structure should have optimum orientation and tilt angle. We'll come to this, but the point of emphasis here is optimum orientation and tilt angle to maximize power output, and all shading should be avoided. The structure will typically be made from aluminum or galvanized steel. Painted steel or wood are also options, though such structures will probably require more maintenance over the 20+ years lifetime of the solar system. Now, for some of us that may want to use wood to do our solar as opposed or as against galvanized steel, we need to bear in mind that this solar panel has a lifetime of more than 20 years. And the question you have to ask yourself, if you use wood, can that wood last for up to 20 years? If it cannot last up to 20 years, then there's going to be a problem. It's either you need to go back after some time to replace those wood, or you need to do more maintenance on those wood. And that's why it is recommended that you use a galvanized steel that can last for the same lifetime of that solar panel. So this is just a pictorial example of some of the mounting structures that we've talked about. So this one is a roof mounted, commercial rooftop mounted solar panel. And then the one in the middle is a house rooftop fixation system. And they have a ground mount fixed support. So for some, please mute yourself. Who is speaking? Can you mute yourself?
Also, if that not finish around by Monday, I would have been there, but I'll be there by 1.
Engineer, please mute yourself. I think that is coming from your own end. Okay. So this is just a pictorial illustration of the mounting structures. I also want to talk about trackers. Sometimes you may need trackers, even though the cost of using trackers, it's not viable, because the extra energy that you're going to generate for using trackers may, in most cases, outweigh the cost of that tracker. So in most cases, we don't use trackers in Nigeria. Okay, not that you cannot use tracker, you can use tracker, but you're looking at the economic viability of using trackers. So tracker, what tracker does is that it follows the sun. Because when you're doing a fixed solar installation, it does not move, it just has a fixed position. But if you have a tracker, what tracker does, it enables that solar panel to follow the sun. And the sun rises from the east and sets in the west. The solar panels follows it, and then it makes sure that it harnesses the maximum amount of energy that the sun can generate. So this is the tracker that I talked about. There are two kinds of tracker. You have the single axis tracker. Horizontal direction, as well as rotation of the panels. So let us look at some physical aspect of the PV system. So the PV cell, we are going to pay more critical attention to the PV cells, how it generates electricity, and how it can be optimized. Okay, so let us pay more close attention to this. So the electrical power P for DC system measured in watts is the product of voltage represented by V measured in volts and current represented by I measured in amperage. So the long and short of this whole statement is P is equal to V times I. A lot of us will have been familiar with this formula. P is power, V is voltage, and I is current. So power is a product of voltage times current. Voltage times current. Now let me ask a simple question, because I want to also be sure that we are also following this training. If voltage is 230, if we have 230 as a voltage, and they will have current as 0, what becomes the power output? One or two persons can just unmute themselves and speak to the mic. Power becomes 0. Thank you.
Power becomes 0.
Okay, thank you very much. Okay, thank you very much. I just want to confirm that we are following the logic here. because we get to a point where it may become a little bit complicated. So if we understand this basic, we can as well understand it when it's getting a little bit of a complication. So under normal sunlight condition, the PV cell's voltage remains fairly constant. However, the current is very sensitive to sunlight. High solar irradiance will produce a higher electrical current. Low solar irradiance will produce low electrical current. Now, once the sun comes out, your voltage, this voltage, once the sun is out, this voltage is almost constant. It remains almost constant. Okay, but this current depends on the intensity of the sun. This current I is dependent on the intensity of the, so once the sun increases, the current will increase. And once the current increases, your output power will also increase. If the current reduces, if the sun, if there's a shadow, if there's a slight shadow on the PV model and the intensity of the sun is reduced, this current will reduce and your power will also drop. But this your voltage will almost remain constant. Almost, not that it's remain constant, but it almost remain constant. So it's important that the intensity of the sun affects the power generation of the PV model. So you need to know that. So the surface area of a PV cell also affect the electric current output. A cell with a large surface area will produce more current than a cell with a small surface area. Of course, this is a simple logic. If you have more PV panels, you generate more electricity. If you have lesser PV panels, you generate less electricity. So this is now dependent on the surface of the PV. So if you have more PV panel, you have more surface area. If you have a lesser PV panel, you have a lesser surface area. So that is just the factor that is responsible for generating more electricity or generating less electricity. So thus, the two main factors that affect the output of a PV cell are the intensity of the sun falling on it. Remember when I told you that if the sun increases, if the intensity of the sun increases, the current will increase and then your power will increase. So that is one factor that affects the output of a PV model. And then the second factor is the size of the PV cell. The size of the PV cell. If you have more PV cells, you have more power. If you have less number of PV cells, you have less power. Okay, so now let us look at the electrical characteristics of the IV curve. IV curve means current voltage curve. That's IV curve, current voltage curve. If you look at most, in fact, if not all the PV models in the market, if you look behind them, you will see so many funny abbreviations. So I'm going to explain all of what those abbreviations means, because they are very, very important. If you're going to be doing a solar project, it's very, very important you understand some of those abbreviations and how you can actually read them and then use those values there to do your designs. So the IV curve, this IV means current voltage curve. Okay, so the IV curve describes an important electrical characteristics of a PV cell. At any given time, a PV cell is operating with a specific current and voltage, which lies along the IV curve. So look at this red line here. This red line is the IV curve, okay? The red line in the chart is the IV curve that we're going to be studying, okay? But we are going to see how current and voltage affects this IV curve. So we're going to be discussing that now. So the IV curve shows the current. The current is represented by I, which is produced over a range of voltages. Now, capital ISC represents the short circuit current. So when you see ISC, it represents short circuit current. And what short circuit current means is the value at which the current is at maximum and the voltage is at 0. Now let us look at the IV curve, this red line. Okay, this red curve that we're seeing, okay? Now, if the vertical axis, this is the vertical axis. So this vertical axis represents the current, and then the horizontal axis represents the voltage. Okay, I take that once again. The vertical axis represents current. The horizontal axis represents voltage. So at the point, now this red line is the current. This red line we're seeing is the current at different voltages. So if this red line is the current, at what point is it maximum? At what point does it produce the highest current? So if you look at this line, you find out this is the point where it produces the maximum current. So at this point where it produces the maximum current, let us look at what the voltage is. You take it down. If it traces down, you see that the voltage is 0. This is voltage and this is current. I hope everyone is following this. Now, if this is current, now this is the maximum current that the PV can produce. And at maximum current, the voltage is 0. At the minimum, at the lowest current, that is when it's producing 0 current, the voltage is highest. That's where the voltage is highest. Okay. Now, what this means is that this point that we had, this, okay, this point that has a red tip here is the point where we call open circuit voltage. Open circuit voltage. Whereas this point where the current is highest is where we call short circuit current, that is ISA, whereas this point is open circuit voltage. So open circuit voltage represents the open circuit voltage, right? That is the value at which the voltage is at maximum and current is at 0. Current is at maximum and voltage is at maximum and current is 0. Now, I'll give you a typical example of what this open circuit voltage is, okay? If you have a pure resistive load, sorry for some of us who does not have a background in electrical appliances or electricity, please, I crave your indulgence. I just want to use this to explain a point, okay? If you have a purely resistive load, and an example of a purely resistive load is your heaters, your water heater, your boilers, your kitchen hot plate. These are purely resistive load. So we have a purely resistive load. What that means that the current that is flowing those load is 0, but voltage is maximum, and that's why you place your hand, it cannot shock you because it's converting all the current to heat. Okay, so when current is 0, your voltage is at maximum, and at that point you have what we call the open circuit voltage, and that's what is happening at this point where you have the VOC. Okay. So now let us relate what I've just explained with this equation. This power is equal to voltage times current. And this is why I wanted us to understand what this equation really means, right? So if this current is at maximum, if the current is at maximum, which is here, it is maximum. And when it is at maximum, voltage is 0. What becomes the power output? It becomes 0. Now we want to maximize the voltage. If we maximize the voltage, this is where the voltage is maximum. But at maximum voltage, the current is 0. The power also becomes 0. So we are looking for a point where the value of voltage and current will give us the maximum power output. I take that again. When the current is maximum, the voltage is 0. And if the voltage is 0, the power output will become 0. Now, when the voltage is maximum, which is here, the current is 0. And when the current is 0, the power output will also become 0. So we are looking for a point along this red line, okay, where the combination of voltage and current will give us the maximum power output. Is there any confusion here at this point? Is there any confusion? Does anyone have any question? Does anyone need further clarification on this?
No.
No.
Okay. Okay, thank you very much. So now we now proceed to the power curve, because we are looking for a point where we are going to get the maximum power on this red line. Since if you have the maximum current, voltage will be 0. If you have the maximum voltage, current will be 0. So we have a problem. So the power curve of the PV cell is shown in the blue line, this blue line. This is the power curve, okay? This line shows electric power produced over a range of voltages. Under normal operating conditions, the curve grows and contracts along both the current and the voltage axis. So this blue line is what will help us to determine at what point in this red line we are going to have the maximum power, okay? So now the maximum power on this blue line. So we have to look at the maximum value of this blue line. Now the maximum value is here, is at the knee. Okay, this is where you have the maximum power. So we trace down at the point where it meets this red line. If you trace it down, this is where it meets the red line. So at this point, this is the point where the combination of voltage and current will give us the maximum power. That is this point that we have here. If you move further down, what are you going to be reducing? If you move further down, what are you going to be reducing? Is it current of what is okay? If you correct, if you move further down,
current is reducing.
Exactly.
The current is reducing.
Correct. If you move further up, what are you going to be reducing?
Voltage.
Exactly.
Voltage.
And if you reduce,
Voltage.
if you keep exactly correct. Thank you very much.
And current is increasing then.
Exactly. So if you move further up or further down, you now the power will ultimately drop. So this is the point where the combination of current and voltage will give you the maximum power output. I'm struggling to get my mouse back. Okay. Just a moment. I'm trying to get my mouse up to the screen. Can you since my mouse seems to have been frozen here, can you see my you can still see my screen, right?
Yes, you can see. Yes.
Yeah, but my mouse is no longer moving.
Just keep explaining.
You have to close the document and reopen it again. I think so.
Okay, let me just try.
I think he can keep explaining. We can follow. When he describes, we will follow.
I think you can keep explaining. We will follow.
Or you
Keep
use the touchpad.
I think the PDF is there. Let him continue.
Plug the mouse and plug it back, and let's see.
Yeah, I'm trying to get that.
It's working now.
No, I'm the one working now. Chima, let me scroll for you while you work on it.
Okay. So Uche, you're the one sharing the screen now, right?
Yes, I'm sharing mine.
Okay, though it would have been better for me to. Okay, no, go back to the head. So the power curve, I'm talking about the power curve now, okay? So the power curve of the PV cell is shown in the blue. Okay, I've explained what that power curve is and how we arrive at the maximum power that we can generate by combining the voltage and the current. Now, this point is what we now refer to as the maximum power point. If you go to the market for charge controllers, you will hear things like MPPT, okay? That's what it simply means, that those charge controllers can actually give you the maximum power point automatically. There are two kinds of charge controllers in the market. So you have the MPPT and you have the PWM. The PWM, that is the pulse width modulation. It does not do the power point tracking. It does not do the maximum power point tracking. So the MPPT does the maximum power point tracking. That's the meaning of that MPPT. So it gives you the maximum power from the solar panel automatically at all points. Okay. So now, if we reframe this power equation, that is P is equal to voltage times current. What you're going to have is P maximum power is equal to V maximum power times I maximum power. Maximum power point.
Hello, Chima.
Can you hear me?
Yes, please go. The PWM, can you explain it? PWM, please. Sorry to disturb you.
Okay. I thought about PWM. That is a different kind of charge controller. There are two different kinds of charge controllers in the market. There is MPPT charge controller and there's a PWM charge controller. PWM means pulse width modulation, right? So it's a different kind of charge controller, and then we have the MPPT. MPPT means maximum power point tracking. Okay, so the more efficient charge controller in the market is the MPPT charge controller, and that's most common. So I'm only trying to explain to you the meaning of that MPPT and why it is called MPPT.
Okay.
Yes. Uche, someone is saying that you should maximize the screen, because you're the one who is sharing at this point. Okay. So you can move to the next screen, please. So now let us look at the factors that are affecting the power output of a solar system. The factor that affecting the power output of a solar system. So there are three critical factors which affect the instantaneous power output of a PV cell or the module. Now, one of them, of course, we've touched on some of them, but let me just reiterate this thing. So the first one is the solar irradiance, incidence on the surface. The amount of sun that is falling on the solar panel, it affects the amount of power that can come out from that PV module. Okay, that's the first one. Then the second one is the temperature of the PV cells. The temperature of the PV cells affect the amount of energy that you can get from a PV module. If the temperature is high, it reduces the amount of energy you can get from that PV module. Okay, so if the sun radiation is high, it will increase the amount of energy you can get. But it looks like a counterproduct, because if the sun intensity is high, you would expect that the temperature will also be high, right? So these are the factors that affects the output of a solar PV system. So you cannot have a solar PV system that is rated 400 watts and it will give you 400 watts. So because of the difference in this solar irradiation and temperatures, it will affect the output. So if you have 400 watt rated PV system, in many cases, you may be able to get up to 75% or 80% of that power. You will definitely have losses because of these factors. Okay, so the third one is electrical load resistance connected to the PV cells. This is another factor that affects the power output from the PV system. Move to the next one, Lucia. Hello? Which is just a moment. Let me try and see if I can reclaim this my mouse, because it's really important that I point out to the point where I'm talking about in the presentation.
It actually started work. Hello, it actually started working at the time.
No, it's from Uche. It's Uche that is now sharing his screen.
Okay,
I'm not the one sharing my screen at this point. Yeah. So just like 30 seconds. Let me do this.
Maybe you need to change the battery of the mouse.
Hello, Ushe.
Or maybe you unplug the mouse.
No. Let's just continue. I will log in from another system but let's continue now. I'm trying to come up with my second system so I can take it off from there. But let's continue here while I'm doing that. Okay, so the impact of irradiance. Now, remember we've identified 3 items that affect the output of the solar system, and one of them is irradiance. So let us look at how irradiance affects the power output of a solar PV system. Now, the output power of a PV cell or PV module directly depends on the solar irradiance incident on the surface. As irradiance G, now we represent irradiance with G. As irradiance G increases, the current I increases due to an increase in the level of the photovoltaic effect. So if the sunlight increases, what it means that the current increases, not the voltage. Current increases. The voltage remains almost the same. So if the voltage remains constant and current increases, what happens to the power output? It would increase.
Increase, yes.
Okay. So if the current reduces, the power output will ultimately reduce. So it follows the sun. If the sun increases, the output would increase. If the sun reduces, the output would reduce. Okay. So now let's talk about the voltage. Now the voltage, on the other hand, varies slightly with changing irradiance. Okay. This means that as soon as the sun illuminates the surface of the cell or module, the voltage rises to a value that is close to the open circuit voltage, regardless of a change in solar irradiance, such as shading or from passing cloud or voltage. The voltage will fluctuate only slightly below that open circuit range. So what that means, look at the diagram by the right. You see by the vertical side of it, you have what we have is the current. Okay. Then on the horizontal, we have the voltage, just like in the other illustration that I made, which is someone is at the waiting room to admit. I can't move my mouse here. Okay, thank you. So now, if you look at that vertical side, you can see that, remember, we have represented the irradiance as G. Okay, so at the lower part of that graph, you see G is equal to 200, G is equal to 400, G is equal to 600, up until you have G is equal to 1000. So you can see that as the irradiance changes, you can see that there's a huge difference in the amperage, in the current, right, on the vertical side. But let us look at it on the horizontal side. You can see even with the changing irradiance, the voltage only changes slightly. It does not change much, right? Yeah. So this is just to illustrate the impact of irradiance on the energy output. So the moment your current increases, it increases your power output.
Sorry, sir. From the drawing, where is the open circuit voltage you are seeing from the drawing?
From this very drawing. Now the open circuit voltage is the voltage at which the current is 0 and voltage is maximum. So unfortunately, I can't move my mouse. Now it's at the lowest point of the horizontal side where you have, okay, all those lines that terminate at 20. You see where you have the 20 on the horizontal side? You see yes, 20. Yes. Yeah. So all those lines that terminate at that above those 20. So that's the point where you have the open circuit voltage, and that is the point where current is 0.
Okay.
So if there's any further question, if not, so the current, however, increases in direct proportion to the irradiance, only reaching the module full current under strong irradiance. I've explained all of this. We should move to the next one, please. So let us look at the impact of temperature. Now we've talked about irradiance. If anybody is not clear how irradiance affects the output of a solar panel, please ask your question, or I will move to how temperature affects the output of a solar panel. Now, the performance of a PV cell also varies with temperature. Since PV cells and modules cannot convert 100% of the absorbed light into usable electricity, some of this energy is lost in the form of heat, which causes the temperature of the cell to increase. This is normal. This is a normal part of operation of a PV cell and cannot be avoided. Now, let me just explain what this is. If you look at this diagram by the right, Okay, it's similar to the one we have before now, but with increasing temperature. The one we have before now is increasing and decreasing irradiance, but this one is talking about temperature. So you can see that we started from temperature of 25 degrees, and then it moved up until the temperature of 75 degrees. Now you will notice that, now remember that the horizontal line is the voltage and the vertical line is the current. Now look at the change in the voltage as this temperature changes. You see that it is significant on the horizontal side, from 25, from minus 25 actually to 0 to 25 to 50 and to 75. You can see that there's a significant change as the temperature changes on the horizontal side. But on the vertical side, it is almost insignificant. It changes slightly. Everything is close to that 3. Okay. So the change in temperature does not affect current so much, but it affects voltage so much. So if your temperature increases, it reduces the voltage of the solar panel. And when the voltage of the solar panel reduces and the current is kept constant, what happens? The power will reduce. Okay. Is that clear? Remember our P is equal to V times I. Okay, exactly. So remember this equation. So if the voltage,
Hello, I think we lost.
Are you there?
Yeah, I think we lost him. Let me try to pause the recording.
Okay. Wow. Okay, so can you still hear me? Can everyone hear me?
Perfect, perfect.
Sure,
okay,
sure.
Yes. Okay, great. Yeah, so this is where I was trying to discuss about how temperature affects the power output of the PV system. And I said once the temperature increases, when the temperature increases, please, if you're not speaking, kindly mute yourself. Regina Kabiru, please mute yourself.
Being recorded.
Okay, thank you. So the voltage the temperature affects the voltage of the PV system, and once the voltage is being affected, it ultimately affects the power output. So under normal condition, the PV cell will always operate at a temperature higher than the ambient temperature. The ideal operating state for maximizing power output is higher irradiance with lower temperature. Such conditions are rare. My voice is echoing.
It is because in the room where you are, there's another system connecting. So there's a jam.
Let me turn it off.
Yeah, you have another system connected, so disconnect that one.
Okay, I think it has stopped, right?
Yeah.
Okay, thank you. Okay, so I'm trying to say that under normal conditions, a PV cell will always operate at a temperature higher than the ambient temperature. Now, what this is trying to say is this: if you measure the ambient temperature of the air, okay, assuming that the ambient temperature of the air is 35, for example, the surface temperature of the PV module will not be 35; it would be higher than 35. Just like if you look at the roof of a building that is zinc, if the temperature of the ambient temperature is 35, if you touch the zinc, you will notice that the zinc is hotter than the ambient temperature, right? So if you want to know the operating temperature of that PV module, it is not ideal for you to just measure the ambient temperature, rather the surface temperature of that PV module. Okay, so that's just what I'm trying to explain here. So impact of load resistance. Remember, we have mentioned 3 things that affect the output of PV cell. We've talked about irradiance, we've talked about temperature, and this is resistance of the load. Now, an electrical load connected to a PV module will determine the point on the PV module IV curve where the module would operate. An electrical load could be a light bulb, a pump, the grid, or a battery. If there is less sunlight available, then the load will pull less current. Now, the voltage across the load and the amount of current that the load pulls from the module is determined for a given irradiance, and therefore for a given IV curve by the equation. Now, this is just the equation that relates the resistance and the current and the voltage. Now, remember when I talked about open circuit voltage and I made a reference with the resistive load, the heater that we use in our house. Now, those are purely resistive load. Now, depending on the kind of load that you have connected to that solar panel, it will determine the point, it will determine the MPPT point, the maximum power tracking point. Okay, so the maximum power tracking point is related to the kind of load that you put on that solar system, and that's where the resistance have effect on the output of the solar panel. So note that if batteries are connected to the PV modules, as in an off-grid system, the batteries will determine the voltage at which the PV modules would operate. Now, the module's output current would then correspond to the module IV curve at that voltage. So for most off-grid system applications, remember that we have batteries. So it is those batteries that will determine the voltage at which the current would, it will determine the voltage at which the PV will operate on the IV curve, right? Just like I have explained that if you have a resistive load, that resistive load will feed back to the point where the MPPT would operate. So if you're using a battery system, the battery will not determine the point at which the MPPT would be. That's what I'm just trying to say here. And that is how resistance affects the output of a solar panel. So let us look at standard test condition. This is known as STC, standard test condition. So due to the variability of power output of PV cells, depending on parameters such as irradiance, temperature, resistance, the performance of different cells operating under different conditions cannot be compared easily. So in order to enable meaningful comparison between PV cells or PV modules, the rated output of the cell or module is always measured under specific conditions. These conditions are standardized across all testing facilities worldwide and are called standard test condition. So if you look behind the nameplate of your PVs, you will see STC. You see so many things at STCs. So the test that was conducted on those PV models was done under an STC condition. And what are these STC conditions? Now, the STC conditions is, one of them is the light spectrum or air mass is at 1.5. Then there is what we call irradiance. That is the amount of sunlight that is falling per square meter is 1,000. And then the cell temperature is 25. Remember that we've said that irradiance and temperature affect the power output. So all of this has been standardized at 25 degrees centigrade and 1,000 watts per meter square. And then this test was conducted, and then the capacity of the solar panel was established. So if you see a solar panel that has 400 watts rated on it, that 400 watts is tested at 1,000 watts per meter square and at 25 degrees centigrade. So all things being equal, if you take that solar panel and install it in a facility, and that facility is receiving 1,000 watts per meter square, and the temperature of that solar panel is 25, you would definitely get 400 watts from that panel. But if you move away from this standard test condition, then you either have less power or even more power. It could be surprising that you could have a solar panel that is rated 400 and you could get over 400 power out of it. It is possible, okay, depending on these conditions. Okay, so remember when I said that if the temperature increases, it reduces the power output. Now think about it the other way. What if the temperature reduces? So instead of 25, the temperature goes below 25 degrees centigrade. What it means that the voltage will increase. And as the voltage increase, you get more power. And at that point, you'll be getting more power than the rated capacity of that panel. Okay, because that panel was tested under 25 degrees centigrade, and you're not doing less than 25 degrees centigrade. What do you mean? That you get more power out of it? And it is only in those conditions that the rated panel, the capacity of the panels can be exceeded. So each finished PV cells or PV modules leaving the production line undergoes a flash test. It is exposed to a flash of light under careful control of the Stc parameters, lasting only milliseconds, and the output performance is recorded. So subsequently, the cell or modules are sorted and sold according to their rated power. The rated power is measured in units of watts peak or kilowatt peak and refers to the rated power at standard test condition. Now let us look at what temperature coefficient. The temperature coefficient shows how voltage, current, or power output of a PV cells or module changes with changing temperature. Now remember what I've said, that if temperature increases, if the temperature of the PV model increases, the voltage will reduce. But what is the rate of that reduction in voltage? If temperature increases by 1 degree centigrade, how much voltage would you lose? If temperature increases by 1 degree centigrade below, if the temperature goes below 25 degrees, which is the standard test condition, if it becomes 24 degrees centigrade, how much voltage do you gain? If the temperature increases from 25 to 26 degrees centigrade, how much voltage do you lose? That is what temperature coefficient tells us. Okay, so the module datasheet gives temperature coefficient known as Tc for open cycled voltage under standard test condition, and as well as the short cycled current under standard test condition, and the power of the maximum power point under standard test condition. There are some terms that we need to understand very well here, so we don't confuse them, like this MPPT or PMPP, the VOC, the ISC. We need to understand these terms very well, and I've explained what they mean, so don't confuse them. If you look at the labeling of your solar panel, you will see all of this. They will give you all of these parameters. They will give you everything. So the voltage temperature coefficient is the most common one used. And the reason why it is the most common one that is used, because the temperature affects voltage a lot. It doesn't really affect the current, it affects the voltage a lot. So if the temperature is increasing, we need to know how much voltage we are losing. So inverters and other devices such as charge controllers can be damaged by the modules or the string voltage that exceed the specified input voltage to these inverters. So conversely, if the voltage is too low, this can cause system underperformance. And if the voltage is too high, it can damage the inverters. So this is an example of a temperature coefficient. Example of a temperature coefficient is -0. So look at the value I'm referring to here, -0.156 volt per degree centigrade. So for every temperature increase beyond 25 degrees centigrade, you will lose 0.156 volts. This is a typical example of a temperature coefficient. Or you could have it in form of millivolts, or you can have it in form of percentage. So for every temperature increase, you lose certain amount of voltage. And when you lose certain amount of voltage, your power drops. That's what it means. So there's also a current temperature coefficient, but the current temperature coefficient is not significant, so we neglect it. We don't always pay so much emphasis on. Okay, look at what this value is. This is a temperature coefficient. So 0.0029 is negligible compared to 0.1. This is something huge. Okay, for every degree rise in temperature, you lose this amount of voltage. Okay, so the voltage is really, really important when we're talking about temperature. So this is also power temperature coefficient. So this tells us how increase in temperature affects the overall power output. So this is just a simple way we can do some of these calculations. I don't want to spend so much time. If you understand what the VOC means and the VMPPT means and every other thing, if you understand how they relate, you can easily do any calculation that comes along with this. So let me just explain this. Assume the following data. The yearly daytime temperature at a location ranges from minus 10 degrees centigrade to 45 degrees centigrade. A PV module is being installed, which has the following characteristics. So you have the VOC, that is open circuit voltage, at 43.24 at standard test condition. Then the maximum power point voltage is 35.35, still at STC. A temperature coefficient of minus 0.168636 volt per degree centigrade. Now, the question might come, okay, let me go to the next slide. But what this means that for every degree temperature drop below 25 degrees centigrade, the voltage will rise by 0.168636. Similarly, every degree temperature rise above 25 degrees, the module voltage will also drop. I've explained some of this. So this is just a calculation exercise. It's not a difficult one. These are simple calculations. So this one is now saying the maximum open circuit voltage will be produced at the lowest. Okay, now this is the question. The question is in red. What will be the maximum open circuit current produced by the module? This is just a simple question that is calculated. Now, the maximum open circuit voltage will be produced at the lowest ambient temperature. So when remember that when the temperature reduces, the voltage increases, and that is when you're going to have the maximum voltage. Okay. So this what we did here was, now this is the lowest temperature that we are given in the characteristics here. So you can see that the module is installed in a location with minus 10 degrees centigrade up until 45 degrees centigrade, and they are now asking us for the maximum open circuit voltage. The maximum open circuit voltage will occur at the lowest temperature at minus 10 degrees centigrade. Okay. So what this calculation essentially does is that you now determine the difference. The standard test condition is 25 degrees centigrade. And the point that we want to calculate is minus 10. What is the temperature difference between 25 and 10? If you get that difference, you multiply it by the coefficient. Okay, if you multiply it by the coefficient, which is 0.1686, if you multiply it by the coefficient, you add it to the voltage at the standard test condition. The voltage at the standard test condition is 43.25. It was given in the statistics here. So look at this here, 43.24. This is the voltage, okay, at 25 degrees centigrade. But if you move below 25 degrees centigrade, this voltage will ultimately increase. And that's what they are asking us to calculate, okay? So when we do that calculation, you will now arrive at 49. So your voltage is now 49. Remember that at standard test condition, this voltage is just 43. And now you're having 49. When you're having 49, what it means that your power would now increase. I hope it's clear. Is anyone lost? Because if you understand this basic calculation here, you can then understand every other one that is below it. Does anyone have a question with this calculation?
Yes, sir. But this coefficient, is there any specific curve where we will see these values?
It will be provided for you by the PV manufacturer. So when you look at if you look at the data label behind the PV model, you will see this coefficient. It will be provided.
Okay.
Yes, it will be provided. So let me just rush.
Hello, excuse me, please.
Okay. Okay.
Please, before we go, the question didn't specify at what temperature. Because I can see you are using 25 degree You didn't specify at what temperature as it is. Can you shed more light on that?
Okay, so the question is asking us for the maximum voltage at the where we are going to get the maximum voltage of that PV module, given the temperature of the location where it wants to be installed. Maximum open circuit voltage means that current is 0. What is the maximum voltage that can be gotten from that system? Now, by standard test condition, the voltage that was given to us is 43.24 at standard test condition. And remember that standard test condition is at 25 degrees centigrade. It's a standard.
Okay.
It's a 25 degrees centigrade. So, and I told you that if you move below 25 degrees centigrade, what happens to your voltage?
Okay. Okay.
No, I want to know.
It increases. It increases.
It increases.
Exactly, it increases. So when your voltage increases and your current is constant, what happens to the power output?
It's an increase.
Exactly. So now, because you're going below 25 degrees centigrade, you will have a voltage that is higher than the voltage at standard test condition, which is 43.24. But if you're now looking at the other side, if the temperature is increasing, if you're not if you're not going beyond 25 degrees centigrade, the voltage will begin to reduce. Is that clear now?
Yes, it's clear. Thank you.
Okay. Okay, thank you so much. So let's just look at orientation and inclination or tilt angle of a PV module. So PV modules orientation and inclination or tilt angle significantly affect the amount of irradiation that the surface receives, and hence the amount of energy that the module produces. So in the northern hemisphere, and now let me clarify this. When I say northern hemisphere, I'm not referring to the northern or the southern or the east or the west coordinates we have in Nigeria. Okay. The world is divided with an equator. Okay. So if you have an equator, you now have one half of it is in the northern hemisphere, and the other half of it is in the southern hemisphere. Okay, so Nigeria is located somewhere in the northern hemisphere, close to the equator, though. There's a figure. I will illustrate that here. Well, these are the factors that determine the angle of inclination and the orientation and the angle of inclination of your solar panels. So in the northern hemisphere, the PV modules should be facing south. And because Nigeria is in the northern hemisphere, if you're doing any solar installation, it should have to face south. So you can go with your compass and then determine where the south is located. That's the south. That's the orientation of your PV module. Now, in the southern hemisphere, it should be facing north. This guarantees the maximum irradiation level on the PV module throughout the year. In region close to the equator, just like Nigeria, the orientation is less important. We are close to the equator, but not as close as this statement is illustrating. If you're on the equator, you can just drop your panel flat, to face the cloud, to face the sun. However, the optimum tilt angle of the PV module depends strongly on the location. I've said this, but the point I was trying to make is even if you're on the equator, in which case you're supposed to drop your PV panel flat. You're not tilting it to the south or tilting it to the north. If you put it flat, you will get the maximum output from the sun. But because you want that PV system to be self-cleansing, so you have to also tilt it to at least maybe slightly so that if any object falls on it, it can fall off. So it is not advisable, even if you're on the equator, to put your PV panels flat. So the optimum tilt angle of the PV module depends strongly on the location. As a rule of thumb, the module should tilt to an angle equal to the latitude of the installation site. Now, two things here, the orientation and the tilt angle. Orientation means that is it going to be facing north? Is it going to be facing south? Is it going to be facing east or west? So we have established that for Nigeria, since we are located in the northern hemisphere, our solar installation should be facing south. That is established. Now, when you're facing south, what is the tilt angle? What is the angle of inclination? What is the angle of elevation? Okay, to that south. That's what we're talking about, tilt angle. That's what we're talking about, tilt angle. And this is telling us that your tilt angle should be equal to the latitude of your installation site. And Nigeria is situated in the northern hemisphere, like I've said before, at a latitude of between 4 degrees to 14 degrees. So if you're going towards the north, you're increasing the latitude. If you're going towards the south, maybe in the rivers, you're reducing the latitude, maybe about 4, 5, or as the case may be. But if you're moving towards the north, you're increasing the latitude to about maybe 10, 11, 12, 13, 14. So, but Nigeria is located in this latitude. So if you're doing your solar installation, your angle of your tilt angle should be equal to the latitude of your installation site. So for Nigeria, it should be between 4 degrees to 14 degrees. Okay, so if you see an installation in Nigeria that is having maybe 20 degrees or more than 20 degrees, it becomes a problem. Okay, now there is a caveat to this. Roof-mounted modules are usually simply installed at the same angle as the roof. Since the extra cost of adjusting the tail angle exceeds the benefit of the extra energy that will be generated. So if you go to do your installation and you're installing on the roof and the roof is tilted at maybe 30 degrees, okay, sometimes you have no option than to install it on that roof because the person may not have a ground space to mount it, but on the roof. You cannot tell the homeowner to go and restructure his roof because you want to install solar panel. So in that case, you're constrained. You just have to install it based on the angle of the roof. But if the choice is available for you to make, you have to install it based on the latitude of that location. In regions close to the equator, the most solar irradiation is captured if the solar PV is flat. This is what I was trying to explain at that time. However, in practice, a minimum tilt angle of 10 to 15 degrees is recommended to allow for self-cleaning. Now, this is a solar panel angle concept, just illustrating the solar angle panel deployment. So this is the northern hemisphere, and this is the southern hemisphere. Nigeria is located somewhere in the northern hemisphere here. So if you're installing your solar panel, as long as you're in the northern hemisphere, your orientation should face south. Your orientation should face south, and that is where Nigeria belongs. Nigeria is somewhere close to the equator, but not on the equator, but we are somewhere here. Okay, if you check it on the atlas, you find that Nigeria is somewhere here. So let us talk about yield estimation. I'll quickly rush this, please. Just give me like 15. This is 12 o'clock already, but I'll quickly rush the remaining. I think we've dealt with the more important part of today's class. But let me quickly rush through this solar yield estimation. So this is just a heat map for Nigeria. Okay, we all know that you have more solar sunlight, more solar available in the northern part of Nigeria than in the southern part of Nigeria. But again, the downside of it is that you also have a higher temperatures in the north. So because you have higher temperatures, it will also reduce the output of the solar panel. Okay. So when the resource person that will take us on the new technology in the solar panel comes, he will explain some of this more to us. However, the practice before now is that we use thin film. Remember when I was introducing the session, I talked about 3 types of solar panel. We have the monocrystalline, we have the polycrystalline, and we have the thin film. Now, the thin film has a higher resistivity for heat. So if temperature increases, it does not so much affect the thin film solar panel. So if you're doing a project and you have the choice or the option to choose between these 3, thin film solar panel becomes more attractive for the north. However, it has a lower efficiency. It has a lower efficiency to convert sunlight to electricity. But in terms of temperature tolerance, it is higher. So we can read up some of this. Let me just go to the point where I feel is important. So this peak sun hours is important. Let me just explain it here before I go to the next slide. As the electricity yield is heavily dependent on solar irradiation, we already know this. It is essential that accurate and long-term climate data are available for the given location. Solar irradiance at a site is often stated in terms of peak sun hours. This peak sun hour is just a simple way to enable designers to calculate the amount of solar energy, the amount of energy that can be gotten from their project. I will come back to this peak sun hours with an illustration, but for now, let's just talk about performance ratio. I've explained this performance ratio before now. When I said that if you have a solar panel that is rated 400 watts and you install it in Nigeria, you will not get 400 watts from that solar panel. You will get maybe 350 watts because 400 watts was in fact, 400 watts is at standard test condition. So in Nigeria, you're not meeting that standard test condition. So you definitely will get less energy from that solar panel. So now the difference between that rated capacity and the actual energy that you get is what we call performance ratio. Okay, so how do you calculate it? Performance ratio is calculated by the actual output, okay, divided by the theoretical output. So the actual output is the amount of energy you actually got from the solar panel, while the theoretical output is the rated capacity in the solar panel. So the solar panel is rated 400 watts. If it's rated 400 watts, then the theoretical output becomes 400 watts. And if you install it and you're getting 350 watts from it, then your actual output becomes 350 watts. So if you divide 400, if you do this division, if you do 350 divided by 400 times 100, you have 87.5%. So your performance ratio is 85.7%. So a low performance ratio indicates a high system losses. Okay, for example, due to high module temperature, reflection of solar irradiation from the module, soiling of the front glass, shading, component failure, mismatched module, and there are so many things that could lead to that low performance. But overall, if your performance ratio is low, it shows that there's a high system losses. So energy yield calculation. So this is where I want to illustrate the peak sun hours that I talked about. Now, the following equation provides a quick and simple way to estimate the energy yield of a solar plant over a particular period. So how do you calculate the energy yield from a solar plant? If you're doing a design, I want to calculate how much energy will you get from this solar system. This is how you do it. Energy yield is represented by E, and it is equal to peak sun hours times the peak, that is the peak capacity that you're getting, times the performance ratio. Remember, I have explained what performance ratio is. So these are the definitions of these terms. The E is energy yield. The peak sun hours is the amount of sunlight that you're going to get in a day, assuming that the sun is at 1,000 watts per meter square. So this peak sun hours is based on the assumption that the sun is out at 1,000 watts per meter square. We may not have it in Nigeria. We may have about 500 watts per meter square in Nigeria. Okay, so if you have 500 watts per meter square for 2 hours, okay, for 2 hours, then the peak sun hour will become 1 hour, because you assume that if the sun is shining at 1,000 watts per meter square, okay, you will get the same amount of energy that you get if it's shining at 500 watts per meter square for 2 hours. I don't know if that is clear. If the sun is shining for 500 watts per meter square for 2 hours, okay, you will get the same amount of energy you receive if that sun were to be shining at 1,000 watts per meter square for 1 hour. Someone raised his hand. Inusa, you raised your hand. You have a question?
Hello.
Hello.
Good afternoon.
Yeah, I can hear you. Go ahead, please.
Okay, yeah, please, sorry. Thank you very much for your presentation. It is quite educative, and I have a question around. We're talking about this PR, like performance ratio.
Okay.
PV. What I'm trying to find out is that, I don't know, based on practical experience, what is the maximum PR being found in Nigeria? Maybe we have maybe in the south and in the north. I don't know whether you have data around that. Thank Thank you. This was
okay. Even though your network was breaking, I think what you're asking is what the performance ratio of the projects we have in Nigeria. Yeah, yes, I can hear you.
So he is saying what's the like baseline value or benchmark value that we use for performance ratio in Nigeria. I think it's about 0.7. I think that's what he's asking.
Okay. Yes. 0.
Let me also use that. Let me also make an appeal. We're overshooting by let's say 15 minutes. I'm sorry. Okay.
I want to quickly. I understand. I want to quickly.
In the next 10 minutes, let's round up. But I also want to appeal to participants that subsequently will not exceed 12 o'clock. Okay. But then it also means that by 10 we'll start from next week. Yes. Thank you.
Okay, so the question that you asked, it's already part of the slide. If you look at the last part of this, you see performance ratio of a PV plant. Now, typically for Nigeria, it's between this range. And now, there are so many factors that affect your performance ratio, like I mentioned before, depending on the temperature, the sun irradiation. Like if you're doing a project somewhere in the southern part of Nigeria, your peak sun hours is less. Peak sun hours is lower in the southern part of Nigeria. In the northern part of Nigeria, your peak sun hours is higher. Okay, so you have more energy yield in the northern part of Nigeria than the southern part of Nigeria. So all of this will affect your performance ratio, but overall, it's between 0.65 to 0.85.
Could you come again on the peak sun hours?
So I said the peak sun hours is higher in the northern part of Nigeria, and it is lower in the southern part of Nigeria. Now, and I say that the peak sun hour, the definition of a peak sun hour is the intensity of the sun at 1,000 watts per meter square. You assume that the sun is out at 1,000 watts per meter square. Let me, just a moment. I think this is illustrated. I illustrated this in the next slide. Okay, so now this is a kind of visual explanation of what a peak sun hour is. So we can visualize the peak sun hours by looking at the area under the solar irradiance curve. This area must be similar to the area of a rectangle with a height of 1,000 watts per meter square. The width of the rectangle determines the peak sun hour. Now, this is the normal curve of the sun, right? It comes out in the morning, and then during the daytime, it hits the peak and it comes down. But you now notice that it didn't get up to 1,000 watts per meter square. Okay, so to make it easier for engineers to calculate the energy yield or developers to calculate the energy yield, we assume that this sun hits this 1,000 watts per meter square. Okay, and they will now compress all of this and shoot it up to this 1,000 watts per meter square. And that's what we have done here. So we assume that the sun comes out in the morning and it's at 1,000 watts per meter square. How long will it stay at 1,000 watts per meter square for the whole of the day before it goes down? So the area that is shaded, this area that is shaded must correspond to the area here. So this is what we call peak sun hours. So if it's between this time and this time, it's 4 hours. But if you look at it here, you would think, you will see that the sun was out for more than 4 hours. The sun was out at 8 o'clock and it now went down at 5 o'clock. Okay, this does not represent the peak sun hours. This is the normal trajectory of the sun. Peak sun hours assume that it is hitting 1,000 watts per meter square. Okay, so if you're doing a project in the southern part of Nigeria, peak sun hours may be in the range of 4 to 5, maybe at maximum 5 hours at peak. Okay, but if you're doing a project somewhere in the northern part of Nigeria, maybe it goes beyond 5, maybe at 6 hours. Okay, the peak sun hours can get up to 6 hours somewhere in the northern part of Nigeria, between 5 to 6, but somewhere in the southern part of Nigeria, around 4 to 5 hours. So this is just an example to illustrate the peak sun hours. It's a simple calculation, it's a simple exercise. I will encourage you to just do it. If you have challenges, you can reach out to me. You can reach out to us on the WhatsApp platform. We can address it. So this is just further examples of a project that is done in the Northern Europe and another one that is done in the Southern America. Okay. So what we do, we calculated the energy yield of both projects. Okay, and we determine now both projects are of the same capacity. This is rated power is 1,000, rated power is 1,000. However, the peak sun hour in in Northern Europe is 1,200, whereas the peak sun hours in the Southern US is 1,900. So because you have a higher peak sun hours in the Southern USA, okay, and yeah, because you have a higher peak sun hours, you have a higher amount of energy yield, okay. Now look at the performance ratio in the Northern America. You have a higher performance ratio of 0.8, but in the Southern USA, you have a lesser performance ratio. But this peak sun hours, the difference in their peak sun hours is so huge that you have more energy yield in the Southern America. So if you're to do a project in these two regions and you're going to spend the same amount of money, but there are some variables that you cannot control, which is the peak sun hours and all of that, we ultimately want to do the project in the Southern America because you have more energy that you can sell to make more money than doing it in the Northern America. I just rushed through this example, but when you go through it, it's self-explanatory. So let me talk about load profile. When you're doing your solar design, one important thing to look at for is your load profile, especially when you're doing for an off-grid system. For an off-grid system means that you must provide solar system that can meet the peak of that of the load. That's what it means. And if you don't know the peak of the load, then you cannot do that design. Okay, so it's important that you understand the load profile. So for a successful electrification project, it is necessary to conduct a precise analysis of expected electricity demand. It has significant impact on the design and cost within the project. The system should neither be unnecessarily oversized or undersized. There are so many generators we have in Nigeria that is oversized. Okay, people want to buy generator, they say, my neighbor is using 500 kVA, let me go and buy 500 kVA. It's a lie, they're not the same thing. Okay, so people buy generator based on mere estimate without engaging engineers to do a proper load audit and advise them on the right capacity to buy. So you find out people have generators that are operating less than 30% of the load factor. You have a generator that can do 100% work and you're using only 30% of the work. Okay, this same mentality is what some developers are bringing into the solar system. And the worst thing about the solar system is that it is capital intensive. So if you don't size properly, you waste the capex. If you oversize, you waste the capex. If you undersize, the customer will not be satisfied. He will blame you, he will say that you don't know what you're doing. So it is important that we do this sizing proper. And for you to do this proper sizing, you need to have a load profile. What does the customer want to power? For how long does he want to power it? What is the power requirement of this load? If you have it, you can establish a load profile. In our next class, we are going to go through these examples, how you can establish load profile and then determine what size of systems to recommend. We'll do all of that in our subsequent classes. So, but the important thing here is that you need to have a load profile. That's the most important thing. Okay. So all these are just literature. So this is an example of what a load profile is. So you can see that from the midnight, there is highly significant consumption up until morning hours, and then the consumption begins to increase. And you have the peak at 19 o'clock. 19 o'clock means 7 o'clock. That's when you have the peak. So if you're doing a solar project for an off-grid system, you must size your system, you must size your capacity to meet this peak. Okay. Now that is looking at it from the surface, but you could also provide some advisory, some consultancy here, or some advisory practices here. Okay, so what do I mean? You can recommend to the customer what is causing this peak load. If, for example, there's a particular machine that you're running at this time, could you stop running this machine at this time so that the capex for installing your solar system will come down? Because the higher the peak load, the higher the size of your solar installation, and the higher the capex. But to reduce the capex, you can advise it. If you look at it, if you have this load profile and you see this peak, you can investigate what is responsible for this peak. Then you can advise your customer, please, if there's a particular equipment that you're using that is causing this peak, can you do load shifting? Can you shift this peak to some other time? If, for example, if it's a washing machine, this is a load that you can do at any time. Is a load that is a work that you can do at any other time apart from this period. So you can advise the customer, please, can you do your laundry at 9 a.m. instead of doing it at 7 p.m. Do it at 9 a.m. so that you can have a lower capex to do your project. So this is why peak load profile is important to establish your peak load. Now, this is a daily peak load. This is a month, 1 month peak load. Okay, so I've explained all of this. Sorry, I was saying peak load. This is a daily profile. This is a monthly profile, and this is a daily profile. This is a monthly profile. And of course, in every profile, you can determine the peak load. So for this profile, for this daily profile, this is the peak load. And you must design to meet this peak load. That's what it means. So I think that is it for today. This is my number. You can reach out to me if you have questions. You can reach out to me directly. You can also put it on the platform. You can also reach out to Engineer Uche. Whichever way you choose, we'll get back to you. We'll respond to you. So thank you very much for your active participation. I really enjoyed the class. It is very interactive. Your contributions, your comments, and your questions really make it